Hello guys. Welcome to our channel, where we dive into the fascinating realm of robotics and technology. Today, we're delving into the revolutionary advancements brought forth by ROS2, the robot operating system. ROS2 isn't just an upgrade, it's a game changer. Its enhanced scalability opens doors to unprecedented possibilities, allowing seamless integration of complex systems across various industries. But that's not all. ROS2 offers improved real-time capabilities, empowering precise control and synchronization in critical applications. And with its extensive ecosystem of libraries and tools, development becomes not just easier but more collaborative and efficient. So, join us on this journey as we explore the boundless benefits of ROS2. Subscribe to our channel for more insights and tutorials, and let's embark on this exciting adventure together in the world of robotics. ROS, short for Robot Operating System, stands as an open-source software development kit tailored for robotics applications. It provides a standardized software platform, empowering developers across diverse industries, guiding them seamlessly from research and prototyping stages to deployment and production. ROS incorporates many toolboxes and solutions for processing different data on various levels of a robot, such as for data visualization, logging, perception, robot control, hardware drivers, motion planning, communication, simulation, machine learning, and computer vision. Even simple robots like this one has many interfaces where data is being processed and where communication between other modules happen. For example, this ultrasonic sensor acts as the perception module, which locates obstacles around the robot. This data is maybe sent to a Raspberry Pi microcontroller to be processed. For this, we need hardware drivers, which then calculate the necessary control inputs for the robot. This control data then needs to be sent to the wheel motors. This closes the communication loop, starting at the ultrasonic sensor and ending at the wheel motors. Now let us understand what the ROS philosophy is all about. ROS facilitates seamless communication between individual programs through defined APIs, enabling efficient peer-to-peer interaction. Whether it's coordinating between sensors and actuators or orchestrating complex robotic tasks, ROS ensures smooth communication within robotic systems. Its distributed computing capability allows programs to run across multiple computers, fostering scalability and resilience in robotics applications. ROS supports multiple programming languages, including C++, Python, Java, and Julia, providing flexibility for developers to utilize their preferred language. This multilingual support enables developers to leverage their existing skills and tools, accelerating the development process and facilitating collaboration among multidisciplinary teams. Despite its robust features, ROS maintains a lightweight architecture, optimizing resource utilization without compromising performance. Standalone libraries are wrapped with a thin ROS layer, ensuring efficiency and agility in robotic applications. As an open-source platform, ROS fosters collaboration within the robotics community, promoting innovation and knowledge sharing. Whether you're a student exploring robotics for the first time or a seasoned researcher pushing the boundaries of robotics technology, ROS provides a collaborative environment for experimentation and discovery. But how does ROS work now? How do we store and move the data between sensors, actuators, and other interfaces? Data is processed or contained in nodes, topics, and messages, whereas movement by data is caused by publishers, subscribers, services, and actions. Each node in ROS should be responsible for a single, modular purpose, like publishing sensor data from a perception module, publishing trajectories generated by a motion planner, or controlling the wheel motors, for example. Each node can send and receive data from other nodes via topics, services, actions, or parameters. A node can both publish and subscribe at the same time. Also, a full robotic system is comprised of many nodes working in concert. Topics are a vital element of the ROS graph that act as a bus for nodes to exchange messages. A node may publish data to any number of topics and simultaneously have subscriptions to any number of topics. Topics are one of the main ways in which data is moved between nodes and therefore between different parts of the system. Services are another method of communication for nodes in the ROS graph. Services are based on a call and response model which differs from the publisher-subscriber model of topics. While topics allow nodes to subscribe to data streams and get continual updates, Services only provide data when they are specifically called by a client. You generally don't want to use a service for continuous calls. Topics or even actions would be better suited. Actions are one of the communication types in ROS2 and are intended for long-running tasks. They consist of 3 parts: a goal, feedback, and a result. Actions are built on topics and services. Their functionality is similar to services, except actions can be canceled. They also provide steady feedback, as opposed to services which return a single response. Actions use a client-server model, similar to the publisher-subscriber model. An action client node sends a goal to an action server node that acknowledges the goal and returns a stream of feedback and a result. Consider this robot as an example. An action client sends a goal point for the robot to reach, and the action server directs the robot's movement and response. While the robot pursues the goal point, it sends feedback indicating the distance to the goal. Once the goal is reached, the robot sends a message indicating success as the result. Some additional features of ROS include parameters, bags, and its vast amount of open-source packages. A parameter is a configuration value of a node. You can think of parameters as node settings. A node can store parameters as integers, floats, booleans, strings, and lists. In ROS2, each node maintains its own parameters. Parameters could be the size of your robot, or its weight, for example. The ROS2 bag is a command line tool for recording data published on topics in your system. It accumulates the data passed on any number of topics and saves it in a database. You can then replay the data to reproduce the results of your tests and experiments. Recording topics is also a great way to share your work and allow others to recreate it. One huge advantage of ROS is that you don't need to reinvent the wheel. ROS2 contains a number of open-source packages which are ready to use and highly adaptable to your needs. The ROS community, consisting of engineers and hobbyists from around the globe, share their interest in robotics and their open-source software. Such sister organizations are ROS2 Control, Navigation 2, MoveIt, and MicroROS. Another important feature of ROS2 is the compatibility of different operating systems, including Windows, Ubuntu, and Mac. Also, it comes with a bridge for nodes and packages which were implemented in ROS1, the old version of ROS. Now let us summarize everything we have seen in this video. We process data in nodes, topics, and messages. We can move around data through topics using publishers and subscribers, or use services and actions. Topics are only used in one direction and for frequent or long-term communication. Services have a request and response type of communication, ideally used for short terms. For long-term communication, we should use actions, which consist of a goal, feedback, and result. Last but not least, ROS2 has many features which make your life as a robotics software developer easier. These features include the usage of parameters, bags, a variety of open-source packages, and the broad compatibility of operating systems. This is it for now. Don't miss out on other videos of this tutorial series by subscribing to this channel. Leave a like if this video was helpful. See you in the next video.